Then, we have this demo titled, FSL, a Federated Split Learning Framework over 5G Wireless Communication Networks. It demonstrates how federated split learning can be applied in a 5G environment. This slide illustrates the overall architecture of our Federated Split Learning Framework over 5G. It consists of two main components. On the right, the split learning process allows each user to compute the first few layers of the model locally and send intermediate activations to the split server via a 5G network. The server completes the forward and backward pass and returns gradients. On the left, the federated learning process aggregates the local model's first layers at a centralized server and distributes the updated model back to all users. All communications are performed over open-air interface-based 5G wireless links, ensuring real-time and low-latency training. The entire federated split learning framework consists of three main components. First, the aggregation server. It is responsible for collecting the local model updates from different users and performing model aggregation, which is a key step in federated learning. Second, the split server. This server handles the intermediate activations and gradients exchanged with user devices. It completes the forward and backward passes of the server-side model in the split learning process. And third, the multi-UE program running on the right side. This part simulates multiple user equipments, each performing local computations on their partial models, and then communicating with the split server over the 5G network. First, we initialize the 5G communication system using open-air interface on PC number 1. Step 1. Start the core network, also known as CN5G. This will launch all essential 5G core components, including AMF, SMF, and UPF. Step 2. Wait for all components to fully start. You should see a message indicating that the services are up and running. Step 3. Launch the GNB, or the 5G base station. The GNB connects to the core and communicates with user devices over the 5G radio interface. Step 4. Optionally, launch FlexRIC, an ORAN-compliant RAN controller, for enhanced control and slicing features. Next, we move on to the user equipment, or UE setup. We use two UE PCs, and on each UE PC, we start the UE process. This connects the devices to the 5G base station we launched earlier. Once both UEs are running, we can check their IP addresses using the ifconfig command on each machine. With valid IP addresses assigned by the 5G core network, we can ping each other to test if communication is successfully established between the two UEs through the 5G network. This confirms that the entire 5G data path, from GNB to core network to UEs, is working correctly. Next, we run the three previously mentioned components on separate virtual machines. The aggregation server, the split server, and the multi-UE program are each launched in their own VM environments, to simulate a realistic distributed deployment scenario. This experimental results show that our FSL approach achieves a good balance between accuracy and transmission cost in 5G scenarios. FSL maintains high skeleton extraction accuracy, close to SL, while significantly reducing packet size compared to FL, making it efficient for edge communication. Finally, we gratefully acknowledge the support of the VERGE project and its funding from the European Union and UKRI.